the chair for the ASQ CPID division within ASQ. Thank you all for coming today. Today we have two wonderful speakers, Anya Scottish and Phil Cinto, both from Lubrizol. They're doing a presentation about Q.LIFE. They'll be talking about their complete platform that they've spent. I think Lubrizol has spent about 30 years developing this, and there's a lot of really interesting concepts and ideas that I think can be extended to a lot of various different contexts and industries. It's an extension of the talk they gave from FTC in 25 in Houston this year. But Anya is a research data scientist in the Data Science and Statistics Department at Lubrizol, where she works on interesting applications, new methodologies for different types of data. And prior to joining Lubrizol in 2023, she received her PhD in biostats from the University of South Carolina, and she also holds a certificate in strategic innovation from the Starla Moore School of Business, an MS from Brown University, and a BA from Providence College. And prior and in between the undergrad and grad studies, she worked in industry as a data scientist in a startup company and in a large pharmaceutical corporation. Her research at Lubrizol focuses on high-dimensional data, multivariate statistics, Bayesian approaches, effective computation, and optimization. And Phil Cinto is a senior technical fellow for Lubrizol Corporation and a fellow of the ASA. He holds an MS from Carnegie Mellon in stats and a BS from Cornell in stats and biometry. He's known for applying innovative statistical solutions in industry, practical applied research in supersaturated designs, and statistical engineering and predictive modeling. Some of his accomplishments in the engine oil industry include the founding and developing of the worldwide control charting system for engine calibration, known as the lubricant test monitoring system, and the statistical treatment of product approval data, known as multiple test evaluation procedures. So I think it's an experimental design approach to industry matrix testing and a data-based single technology approach to base oil interchange, known as a single technology matrix. At Lubrizol, he is responsible for the development and co-management of comprehensive formulation modeling, monitoring, and the optimization system known as Q.LIFE. And just as a small tidbit, we're going to hold questions until the end, but please feel free to give them in the chat, and Stephen and I will ask them to Anya and Phil at the end. All right. Thank you.
Thank you, Shane. Thank you, Stephen, for the invite. My name is Anya, and as Shane mentioned, I work at Lubrizol. My colleague Phil is here. He will help me do the Q&A at the end. Phil has been at the company since the beginning of the statistics and data science team. So if you have some historical questions, you're welcome to send those. And as Shane said, there is the chat. You can put questions there. It also says you can put a fun GIF. So if you like those and you want to send some, I like those too, and they will be welcome. All right, so let's get started. I'll talk for about 40 minutes or so, and then we'll have a discussion and questions. So today I will be, and I'm looking over here, it's my second screen at the slides. I will be talking about predictive modeling in general, how we do that at Lubrizol, monitoring said models and assessing them. And we have that in something that we call the Q.LIFE platform. And we use that to make chemical formulations at Lubrizol. So I'm presenting today. Phil helped put together these materials and also just the Q.LIFE platform overall. Minji Kim was our intern this past summer. She helped with the uncertainty quantification. Kevin Manucheri, a manager on the team, has also contributed to all of this work. I want to give a shout out to the whole department, really, because as you'll see, this is a pretty extensive platform. So there really is, there are a lot of people contributing to this, a lot more than us four listed here. So let's get started here. All right, so today we will talk about the Q.LIFE platform, as I said, the origins of this platform, how it's a suite of interconnected models for effective decision science and data science at Lubrizol. We'll take a look at what the platform looks like. We'll talk about the models that we have in there and the assessment strategies as well for these models. We'll talk about variability estimates of predictions. We'll talk about how these are a bit difficult when we go into cases that are beyond ordinary least square regression. We'll talk about diagnostic tools. Some of them can be residual based, some of them can be based on the similarity between data points. And then really a lesson here that we want to promote is that good model practice is valid regardless of the algorithm that we use. Phil, just a quick note, would you mind muting yourself as well so that I can go through this and then we'll do the questions. Thank you. All right, so let's take a look at this platform section. So before we look at what it looks like, thank you, Phil, I want to give you the motivation behind this. And we'll use an example in engine oils and the engine oil market. So when we're at the chemical formulation company, we try to make, one of the things that we try to make is engine oils. And for each engine oil that we make, or in general, a chemical compound, we want to test that in some way. So for engine oils, we will have laboratories that have literal engines in them, and we'll run our formulated engine oil through this, and then we'll get some test results. And it is through these test results that we're evaluating this. So here, as you can see, in the engine oil kind of graph here or image, we have a pretty big component that is base oil, 75 to 95%, and 5 to 25% are other things, other components that we're going to add. So if you think about all the possible combinations of these percentages that could go into one engine oil, quickly this blows up to be a pretty big problem. We could formulate thousands, maybe hundreds of thousands of oils. And then if you think about all the tests that we could run on them, again, this really blows up. And when we look at these tests, they could have more than one outcome that they're evaluating. Here I have a binary one, acceptable, not acceptable. So very quickly, this becomes quite a large data problem, or just in general, practical problem. So when we try to do this, we realize that, okay, time is limited. These things, testing costs money. We have thousands of formulations that can exceed the capacities of labs. So we find that there is a very strong need for predictive models. But then, as we kind of start thinking in that direction, we also realize that there are challenges also in the modeling area. You can think about, for example, high collinearity among the features of the different oils that we make. Say, an oil is more viscous, then that means that there is another feature of that oil that may be correlated negatively. So if we want to account for both of these aspects of the oil, they're collinear, we need to handle that. Also, we end up with a lot of predictors if we think about how we're going to characterize the oils. There are thousands, hundreds of predictors that we could derive that describe an oil, and so we end up with these collinear, sparse data sets that have a lot more predictors than observations. And so again, the problem grows in complexity. And Thank you. As a result of that, our group has been involved in kind of helping these efforts. So I have here a slide on the data science and statistics group at Lubrizol. We provide sustainable solutions for the needs of our internal and at times external customers. We drive decision making at the company through the use of data. And so, we discussed the problem in this past slide, and we'll discuss the Q.LIFE platform today. But we do a lot more than that. At Lubrizol, we're responsible for developing how we capture data, how we characterize any physical phenomenon into data. We're responsible for quantifying operations with data, also conducting any data operations as well, doing data mining, data-oriented process monitoring, providing predictions through predictive models, but also prescriptions. Nice, a very nice GIF already. Thank you. So prescriptive analytics. And we do that through applications and software. We collaborate heavily with other engineers at the company, and we participate in strategic innovation so that we can continue to propel Lubrizol and the science that we're doing forward into the future. And today, the Q.LIFE platform, it's a model portfolio, also an infrastructure, and it's foundational to the solutions that we provide. And so today I'll be deep diving into that. All right. So the Q.LIFE platform, I think my next slide, yeah. Okay, so in my next slide, I start having some of these more fun graphics, but the Q.LIFE platform is a comprehensive one-stop shop for descriptive, predictive, and prescriptive analytics. It's available 24/7 for anyone at Lubrizol. Also, at times, we use it to answer external customer questions. And Q.LIFE is used to develop formulations, and sometimes these formulations become many times become true products that Lubrizol then puts out on the market. And why is Lubrizol an effective and high-value decision science tool? It's because we have linked and connected models, databases, and end-user systems. We are involved in formulations, in capturing chemical properties, and capturing test procedures, and storing results of tests that are run in databases. We provide advanced statistical modeling techniques, machine learning algorithms as well, and are now also headed into this era of generative AI, as well as large language modeling. We heavily leverage subject matter expertise of other scientists at the company, their prior knowledge, and we definitely rely on peer reviews that we do with colleagues outside of the data science team and inside of the team during modeling processes. And another thing that we do is once we put out, whether it is a model, an insight, anything, any piece of information or tool, we continue to monitor that tool. Here I have models specifically, but this is applicable to most of what we do. We continue monitoring and assessing the models that we provide. And so here, before we talk about the models, I wanted to show you the interconnectedness of all these different systems that we have. So on the left-hand side here, we're kind of starting with more of the database side. So we have some raw data coming in from our commercial side, from the research side, and we have extract, transform, and load pipelines that put all of that raw data into some research databases, some commercial databases. From there, that raw data is taken and we derive chemical descriptors. You can think of those as features that can then be used in modeling. You may have heard the words like covariates or predictors. So we massage the data in the first place here, which leads us to having some data sets. Then we further massage that data into what we call data marts, and that's really when the data becomes quite clean and ready to be used directly in modeling. I want to draw your attention that already in this left-hand side, there are arrows that form a loop to indicate that, and I'm pointing your eyes to the word refresh here. This is not just done once. This is a semi-continuous process that ensures that as new data comes in, it's incorporated into our databases and ready to be used. Now, from our massaged and ready and prepared data, we go into modeling. There we use R and Python. We use open source packages that are available. We use our own proprietary R package that we call QLIFE R. And we prepare models. And all of that, along with some of this data, goes into this large database that we call a Q.LIFE database, and then that goes and feeds into what our end users know as the Q.LIFE platform. So we're gonna go where this arrow points now, but just before, I wanted to tell you high level some of the modeling approaches that we tend to use. You'll notice a lot in the Bayesian area: Bayesian variable selection, model averaging, Bayesian variable assessment, Bayesian approaches with splines, tree-based methods, boosting methods, a newer method called superlearner, an ensemble of multiple models that outputs an optimal average prediction that has been shown to have nice asymptotic properties. So that's for this bluish purple modeling section here. So now, okay, let's go where this arrow takes us and really see what the Q.LIFE platform looks like. So I have 3 blue rectangles, light blue rectangles here. One of them around this quick predict tool, we'll see that. And then we'll see our lab monitor tool, short for lab monitoring, and SimForm, short for a similarity in formulations. So the quick predict section of this Q.LIFE platform landing page is where we get predictions, and then these other 2 sections are where we do the model monitoring and assessment. But really, when a user at Lubrizol goes onto the Q.LIFE platform, this is the page that they land on. They can upload a formulation that they're working on, interested in, or load a previous one or search for an existing one, and then they have access to a bunch of tools. And this is actually cut. There's more even below here, just cut shorter to fit in the slide. But so we'll go into our next section now, and we'll take a look at quick predict, lab monitor, and SimForm. So when we go, say we had clicked on quick predict, we land on a page like this, and this basically tells us for a given formulation, if I were to run this formulation through all of these lab tests, here is the prediction that I would get for a given lab test. And we have over 700 active models available in Q.LIFE, and these over 700 models represent one or multiple tests. So there's a lot there. And again, remembering that earlier slide where we were talking about how big of a problem it is to test all these formulations on multiple lab tests, this is one data-oriented way to abstract that. All right, so before I go into SimForm and Lab Monitor, I want to tell you about the challenges in monitoring and assessment, and then we'll see how we're incorporating these um, solutions to these challenges in our monitoring and assessment tools. When we use something like linear regression, it can be easy or straightforward to get something like a prediction interval or an estimate from a residual variance parameter in the model. But when we go to something like ensemble models, it can become quite complicated. Say a random forest, we've got multiple trees. How do we account for the variability across all these trees? And also, there can be multiple sources of variability in general. I'll take you to the second bullet point here. First, a more straightforward one, variability in feature measurement, measurement error. Going back to that first bullet point, or this dash right here, the model algorithm and the model selection. Okay, we have selected certain features or predictors to be in our model. That comes with some variability. This choice comes with some variability as well. Again, back to the ensembling, because if you think of a tree, we're splitting on one variable and then splitting on another. This allows some types of interactions to form. And again, we have some obscure levels of complexity in these models that do have some variability that is more difficult to capture. And of course, if you just think about labs, lab task protocols, there might be some variability in adhering to that protocol and in recording results as well. So some of these are challenges in not just creating a model that predicts well, but assessing how good that model is. Okay, so a bit more formal here with a slight notation. We can look at residuals, so y minus y hat, and we do have that automated in QLIFE in the LabMom tool. Then, as we were saying, a piece of information that's challenging, but that's really informative, is the variance of our predictions. Again, taking you back to that idea that we have these large matrices of predictors where we have more predictors than observations. We have high collinearity, maybe a lot of zeros. That can really affect this variability of our predictions. Also, if we're using non-parametric models, we might not have a parameter that estimates the residual variance. So we might have a lack of estimate there too. So these are all challenges in assessing models. So, okay, LabMon, our first tool for monitoring and assessing. And let me check on time here. Okay, 20 minutes. This is good. Okay, so something that we can do is, generally speaking, not just at Lubrizol, but as you know, in any modeling, track residuals. But then we wonder, should we do this on the original scale or on a standard deviation unit scale? And if we do that on a standard deviation unit scale, how do we define that standard deviation? We can, in first place, one option is to use an estimated standard deviation from the current model. We could also use that and build prediction intervals for a given prediction from a current model. The formula is here for that plus or minus 1.96, and then that variance piece would be right here. But if we have a new formulation that we're trying to predict for, that's quite different from the formulations that I used to build my model, which are here in this XM, this quantity is going to most likely end up quite large. and possibly too large to be of meaningful use. So again, is it a good idea to scale our residuals based on this estimate of standard deviation for a given point? And then we could also consider, okay, our formulation X nu, where does it fit in relationship to all the other formulations that I've used for modeling? And then we can kind of pick a space in XM that has moderate to high variability, and use that as our standard deviation unit to scale our residuals. So those are all things that we've considered in building LabMon. Okay, and before I have a visual coming up, right before the visual, keeping all of that in mind about how do we quantify that variability, something that we do with LabMon is, one, we monitor, and two, we assess. Monitoring, what we mean by that is we track a new formulation's prediction as it comes in, and then we're able to filter through the options that we have in LabMon to really look at it and make sure it's aligned with the data that we use in modeling. Assessment, we see that as, say, we noticed that there was something unusual with our prediction for formulation X nu. In the assessment phase or assessment features of our tool, we can really drill down into where's the problem and go really deeper and assess that prediction. And again, when we think about these two aspects of our LabMon tool, we have considerations that we want to think about when it comes to our choice of standard deviation estimate. When we're monitoring, should we simply choose to account for greater variability when X nu is quite different, or should we only choose to account for greater variability when there's a problem of some kind? Sorry, for the monitoring, should we consistently choose to account for the greater variability, but then assessment is only if there's a problem? So let's take a look at LabMon here. So here on the y-axis, you'll see standard deviation units. I'll return back to that and tell you more about it. But here's what a visual of our LabMon tool looks like. We've got a graph. We've got our title here. It's a given outcome. It's a model for a given outcome, weighted piston deposits. We plot over time as tests have been completed. We plot the results. Actually, the residual, we plot y, the true result, minus the predicted result, y hat, and this is scaled for this plot in particular, scaled by the standard deviation estimate of the model. So the sigma squared hat, the residual variance estimate for this model. And what we can also see here is, I'm going to point out to a bunch of things. Okay, first, the colored dots. You can see here we've got lab 1, lab 2, lab 3. We can keep track of a given test result and its residual. What lab is it from? Towards the top here, for the monitoring, I mentioned the filter options. We can see, we can filter by lab, stand in the lab. The stand is like the stand on which an engine is propped in. Market segment, this could be an engine oil for a passenger car or maybe for a truck. We can see this filter data table will contain basically all the data that's plotted here. On this graph, we'll also be able to click the no predictions table and see why was something unable to get a prediction. The model name, as mentioned here, it contains the year that it was last updated. We can click everything. We can click the title, get the model details, the predictors that are in said model. We can also click on each data point and open the information that's relevant for that data point. Towards the right-hand side of the graph here, we've got this black gray shaded area. It's a bit hard to see, but it's test results that came after 2021. So those are predictions that we got from the model after the model was developed. So this is each one point of this is an X new from a previous slide. And each point that's not in that gray shaded area was part of the X sub M. And so these are new predictions. And then I'm going to bring your attention to this yellow shaded, orange shaded circle right here. And we can kind of see that, hey, in terms of my residuals scaled, I'm starting to possibly see a downwards shift. The actual test result is less than the prediction. And then we can, in our monitoring, we notice this, and then in our assessment, we wonder, is there a problem or a change with the test? Has the test protocol changed? Has something happened at the lab that has made things differently? Has the model changed in any way, or is the model no longer reflective of reality or what's happening with the test or the lab? Or is it a combination of these three things and other things that I may have overlooked here? And so to conduct that assessment, as I mentioned, we're able to click on each of these points, and it brings us to this part of the LabMon tool that shows a lot more detail. So a lot of things are anonymized here for confidentiality, but you can see that we can see things like some sample numbers, things that allow us to trace back this formulation in our databases. We can see the completion of the test date, back this anonymized stuff back at the top. It's ingredients and the plant information linked to the lab test report on a particular test, linked to the lab test procedure, the logistics, our true test result, so Y, and our prediction Y hat. Requester would be the person who requested a prediction for this test here, location Wycliffe. That's the headquarters of Lubrizol that we put here as an example. So really, once we go into the assessment phase and we're drilling down, we can see information about the formulation, and we can see information about the physical test. You can see the stand as well. So a lot more detail here. And next, we are going to further go into that assessment and talk about our next tool, SimForm. This is, again, similarity in formulations, and it's one of the tools in the Q.LIFE platform. So after we click on a given point, we're able to, as I mentioned, reach all of the tools are interconnected in a way that flows with logic. So this prediction has a problem, we'll open this and we'll go to SimForm. And in SimForm, we'll be able to check predictions versus true test results for other similar formulations. And again, try to drill down into what is the problem, the test, the lab, model, something else. So, all right, I've got my third blue rectangle here to indicate that this is our third tool from the Q.LIFE platform that we're looking at for model assessment. And the way this tool looks, we have a reproduction here to maintain confidentiality and not show the complete tool itself. But what happens is in the tool itself, in the first column of the output, we'll get that prediction that we clicked on that was the problematic one. And we will get next to that the where it says original, that would be the actual test value. And you'll see here the 4.7 and the 6 values that were right here. And in the three next columns, we SimForm has pulled up three similar formulations that we can look at and kind of compare details across. And the way this similarity is determined is through a custom dimensionality reduction approach that we've developed at Lubrizol, and is based on a loss function that we've defined. The more similar a formulation is to this original one, then it will have a lower loss and will be included in this table. And so, say we were looking at this, we see, all right, sim formulation 1, 4.8, all right, kind of similar to our prediction. Sim formulation 2, 4.7, again, kind of similar to our prediction. We see that's lab 1, lab 2, and then when we go to our third similar formulation, 6.2, and that's more similar to the true result. And then we notice, okay, lab 3 and lab 3 here as well. So if I were looking at this, I would then wonder, all right, then this is a path of investigation that I would be interested in taking to troubleshoot this. And so, yeah, this is how we can do some of this investigative work when we get predictions that are worrisome. Okay, so before I return to some of the uncertainty quantification stuff, I wanted to show you within SimForm. This is not here because it's not a screenshot, but there's a place to click that takes us to another tool called the residual check tool. There, again, we can check predictions and true test results and the way they behave across different levels of the predictors that we use in a given model. We can also look at various graphs or various visualizations of the residuals against old and newer test results. We can check for extrapolations. So again, a lot of visualizations and interactive tools are available for us to do this assessment. So a little summary here. We talked about LabMon, SimForm, residual checks. Those are all tools within Q.LIFE to assess y minus y hat. We are continuously monitoring our models through that, and also not only monitoring the models, but we're also always improving these tools that I'm showing you today. We automatically rank models based on how well they predict every month, and if something raises a red flag, we look into it. Models, some of them are updated automatically on a quarterly basis. Some of them are updated every 2 to 4 years. And of course, anytime anyone at Lubrizol raises a red flag about a particular prediction or model, we investigate and improve. Our work in progress, as I mentioned, we're always trying to improve our diagnostic tools. Our work in progress concerns, again, quantifying the variance of predictions and the variance of residuals. Currently, our tool LabMon does not account for that. And again, we understand philosophically and mathematically why that variability is hard to quantify. The shape and characteristics of our data that we use to model can make it difficult to quantify that. Say, if you think of the collinearity in our design matrix XM, that could increase the variance of coefficients estimates, which are then then be used to quantify prediction variability. Sparsity also influences the variance of coefficient estimates. Relative distance of new formulations to the data set that we use to model here, this red point that's kind of outside the modeling space. All of that impacts prediction variance. So we're trying to incorporate all of that. Maybe not required for monitoring a given point, but for assessing problematic predictions, definitely important. We have discussed earlier in the presentation the prediction interval type of approach. We have currently implemented, because of how large that frequentist prediction interval approach can, how large of a prediction interval that approach can give, we have currently implemented Bayesian credible intervals that are based on our sampling within the iterations, the MCMC iterations in our models. Say we had 1,000 iterations. At each of these iterations, we would get an estimate for our beta vector, and we can obtain a y hat for each of these beta vectors and use the 2.5 and 97.5 percentiles as credible intervals for each prediction y hat. So this is what we have right now for some of these OLS-based models. For our tree-based and ensemble models, we've been exploring quite a bit recently. A lot of the methods rely on Bootstrap, which is computationally heavy, time-consuming, and at times can require the data to be shaped in a specific and nice way, which, as I mentioned earlier, we do not always have. But in terms of some of the naive approaches for tree and ensemble methods, if you picture a random forest and we wanted to account for the variability across trees, one thing that happens in the naive approach is that the trees are assumed to be independent, which they are not, most likely not, depending on the data. So then we can move to correction correlated naive approaches, which some of these approaches assume equal correlation between each pairwise set of trees. That also might be a problem. May not be a true representation of reality. And then there are some simulation-based correlation corrected approaches that we found to be really sensitive. The last thing that we've explored is a U-statistic approach. This approach required repeated subsampling of our data set, calculating a U-statistic and obtaining a popular variance estimate, non-parametric estimate. But then when we attempted to do this with our sparse data sets, it's been quite difficult to do the subsampling properly because each subsample might be quite different from another one due to the nature of our data. So that has not worked out quite nicely for us yet. And currently we're exploring this approach called infinitesimal jackknife, which also is based on some bootstrap, but there are some nice properties that we can take mathematical properties that we can take advantage of and kind of reduce the computational burden of that bootstrap. And so I am reaching the conclusion here of this talk. Really, we talked about our Q.LIFE platform, the predictions, assessing models, monitoring predictions, assessing all of that, improving models, improving our tools. But really, something that sticks is that good model practice is good model practice regardless of the algorithm that we use. Really, investigating issues matters. Subject matter also matters. We, as I mentioned, collaborate heavily with engineers and scientists at Lubrizol. We incorporate their knowledge into priors and often use Bayesian approaches where relevant. We consider first principles of chemistry and physics where relevant. As part of good modeling practice, of course, auditing high leverage data points and predictions. We also place importance on using critical thinking for the model to tell a logical story. We do not want to reach a prediction at any cost. We want that prediction to make sense and to be robust. We use peer reviews, collaboration, we investigate residuals, and we document the modeling process that we use in our strategies. And a small point here that we can review during Q&A is checking marginal effects of predictors for smoothness of nonlinearity and interactions. We don't want a small change in a predictor, to cause a huge jump in the quality of our predictions. So my last slide here, takeaways. We at Lubrizol have this platform called Q.LIFE. It's an interconnected model portfolio that's effective for decision making and decision science. It's the backbone for data-driven decision making at Lubrizol. Our ongoing research focuses on quantifying prediction variability and is quite challenging, as we saw today. Q.LIFE has predictive capabilities. I focused heavily on those today, but we do have optimization capabilities. At the FTC conference where I presented this, I joked that I would return the following year to talk about optimization. So I can also return to this webinar to present about our optimization capabilities. And finally, our main lesson, good model practice is crucial regardless of the modeling approach. A few references here. I am going to thank you and open the floor for questions.
All right, thank you, Anya.
Mm-hmm.
Yes, please drink some water after all of that speaking. Well, anyone feel free to put them in the chat, and we'll ask Anya and Phil about this. Phil, could you talk for about a minute or two about like the origins of Q.LIFE and how it's kind of evolved over the years?
Yes.
Yes, absolutely. Can you hear me?
Yes.
Okay, great. As Anya mentioned early in the talk, when you talk about a formulation, there's a lot of different components that go into it. There's millions of combinations. And the tests we run to assess our formulations are very time consuming and they're very expensive. So everybody knows about, I don't even know what it's called anymore because we don't talk about it. Uh, the quick screening that the bio labs always did. The somebody help me out here. with the rapid testing.
The high throughput screening?
High throughput screening,
All
yes.
right.
Well, thank you. We can't do that. Some of our engine tests take up to 500 hours to run and cost $500,000. So we're limited by time and money. So formulators, before they run an expensive test, they would like to know if they're going to get a quote, good, unquote, results. And that's when we started developing models. In the development of the models, we make thousands of compounds, synthesized materials. And as Anya mentioned, we have very few test results. So you can't have a database of 50 test results with thousands of compounds. So that necessitated, and this almost 40 years ago, our look into what wasn't called then, but now what we would call features of formulations. Rather than looking at individual components or synthesized materials, what are the features of those things to cut down on the dimensionality of the data sets? So we might have hundreds of different synthesized detergents we can put in a formulation. If really the performance was related to the total base number of the detergents, I'm picking one feature, that simplifies stuff tremendously. Now, 35, 40 years ago, we were doing these models and trying to develop features. And for those of you, especially who weren't born, each model was published in a memo with an equation, and somebody would have to use a calculator to do a prediction. There were no personal computers or anything like that then. So as everything has evolved, the concept has stayed the same. Let's utilize our test results database to create models for our formulators, which they can use for a lot of different applications. They can check, am I going to have a good result or not? They could check, I got a bad result in the lab, but I thought it was a good formulation. Was it the lab giving me a bad result? So if the prediction validates what they think about the formulation, they can go back to the lab and say, hey, what went on here? We could sit down with customers and say, this is what we have and this is what we anticipate we were going to get. And as computer science and platforms have advanced, we took advantage of that, and rather than just looking at each individual model, we started linking models, because it does no good to develop the best rust formulation and separately the best sludge formulation and separately the best oxidation formulation. It's an advantage to start linking these models. So you want to optimize your formulation across all of these different things to hit certain criteria at the lowest treatment rate, treatment cost, etc. And all of this has happened over the last 40 years. It's happened suddenly fast. It's happened, to quote Casey Stengel, it's happened slowly fast. So that's where we are today. And we joke because if anybody were to sit down and say, I want to start from scratch and put this together, you would almost view it as an impossible task. But since it's been done over the past 40 years, piece by piece, you have to have a good basis. And the basis is We want to take a formulation and empirically assess its capability and use that to drive decision making. So does that kind of answer your question?
Oh yeah, absolutely. These things aren't developed in a singular day, a singular month, year, 10 years, right? It takes a whole bunch of time to incorporate that. And I'm sure people across a large batch of industries that are even in the audience here can align with your thoughts that these systems take a lot of time to develop, vet, quantify, and have actual non-statistical decision makers out there act on your platform as well.
Right. But the key to everything is models. The big thing is AI right now. And if you keep peeling back the layers, you're eventually going to have good models. And what are good models? Anya talked about good models generally come from good model practice. Uh, can't tell you exactly how to develop a good model, but you have to be very careful. If you can avoid overfitting, if you could make sure your models tell a logical story, that's 99% of the equation. There's so many good model techniques now and ways to fit models, and they're all good, but you have to be leery. Maybe taking a conservative approach is a good thing. Use those models to identify fundamental knowledge or cause and effect, and then go verify that either by if an expert says, "Oh yeah, that totally makes sense," go ahead and put it in your model. If the expert says, "No, no, 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 that's yeah," I don't know how we're seeing that, but you just can't see it. And that's why our Bayesian approach to models is a good thing too, because in decision science, if you think Bayesian, where every decision you make is a combination of what you know or what you think you know, and what you see or what you think you see, and you can weight those appropriately, over the long run, you'll come out with the best decisions. Because prior knowledge is important, but it could be flawed, and data is important, but do we have enough of it? And is that data biased and or flawed? So by always constantly weighting the two, you're typically better off in the long run. You don't rely just on what somebody says. You don't rely on the last experiment you ran.
Thank
Absolutely. And I'm sorry to have to cut you off right there, Phil, but it's about 1 o'clock now. Thank you all for attending. Thank you, Anya and Phil, for presenting and talking about your experiences. We really appreciate it.
Oh, you're
thank you
welcome.
for the invitation.
Absolutely. This recording will be available afterward, and if you have any questions, I'm sure we can have you reach out to Anya or Phil about that. So thank you all for attending, and thank you for presenting.
Thank
Thank
you.
Have a great day, everyone.
All right. Bye bye.